lot of interesting stuff happens in the hallway. It happens, you get to walk out of a session and there's a collective experience that you just went through. And so there will be a hallway conversation that springs up discussing the material.
Welcome to Lifetime Management in C++. You're on the Back to Basics track. If you're an expert in lifetime management, you're welcome to stay, but please no heckling. This is going to be a tricky enough subject to cover at a Back to Basics level as it is. So you may have to bear with us at some points. It's a bit of a contradiction in terms. Lifetime management is one of the more complex areas of C++, but it is also something that we should all be fairly familiar with and able to understand what's going on. Fortunately, we are going to look at some things that are going to make it simpler. We'll come on to that. But I do want to emphasize this warning. C++ is a complex language for many reasons, most of it historical, but also a big focus on efficiency, performance, and then mixed with a bit of history as well. Really gives us a recipe for complexity. And this is one of those areas that really shines through. So, C++ is complex. But one of the things that's going to help us to simplify this is understanding that by default, C++ is value-based. It's like a value-first language. It supports other modes as well, and that's where the complexities start to come in. But if we can embrace the value-based nature of C++, it's really going to help. Because values are simple. And let's just look at an integer. We know how to use integers. We can just initialize it with a value. We can assign it a new value if it's not const. And if it's in some scope, we know that at the end of that scope, it's gone away. It didn't have any memory to manage, but you can no longer access it. Simple, nice and easy to reason about. That's what we want. But even looking at integers, we can see there's a few phases that they go through. We've got the construction phase. We're giving it an initial value. We've potentially got an assignment phase where we may assign it to a new value. And that point where it goes out of scope. Okay, there's no actual destructors running, but there is a destruction phase there. It's no longer accessible, and if anything else was referring to it, say by pointer or a reference, that's a problem at that point because it's gone. So those things apply to integers. Obviously, we could do the same thing with something like std string. Std string models a value type in the same way that ints do. So we go through those same phases. We can construct strings with initial values. We can assign them new values. And of course, at the end of their scopes, they go out of scope, they're no longer accessible. But now there is actually a destructor that runs and does some work. One more, vector. Same thing, same phases. Everything is nicely managed. It presents itself as a value type. You can reason about it as a value type, even though under the hood, there's actually more complex stuff going on. So these are our models to follow, ideally. And none of this should be surprising so far, I hope. Even if you're an absolute beginner, this is probably all very familiar. And that's the point. We want these things to be non-surprising. So how many people know this book, Effective C++? So a good number, but not everyone. It's a bit of an older book now, C++ 98 era, but still a lot of wisdom in this book and the follow-up book. And one of the things I remember from this book is this phrase, do as the ints do. You might remember this. So we just talked about how ints work, how vectors and strings are modeled the same way. And this is really good advice. He was talking more about operator overloading there, but also in the context of lifetime management. It's so important to Scott Mayers, the author, that in the second book, More Effective C++, he repeated this phrase. And where he did so, there was a few other quotes that I want to pull out because I think it's really worthwhile reflecting on these. First of all, adhere to the principle of least astonishment. We know how ints work, and so we know how strings work and vectors work to a large degree. We're not surprised by how they manage themselves. But also, recognizing that anything somebody can do, they will do. So they'll throw exceptions, they'll assign objects to themselves, they'll use objects before giving them values. We've all seen this, I'm sure. But we need to be able to work with these things. And all three things that he mentions there are going to come up a bit later, as it happens. And the final quote from this, there's only about 3 paragraphs that I'm pulling these quotes from. It's actually quite dense. So as a result, make your classes easy to use correctly and hard to use incorrectly. Really good advice. But to really follow through on that advice, we need to really understand how lifetimes work and how to manage them in C++ with the tools available. So we looked at ints, strings, vectors. What about pointers? They follow the same pattern. Pointers are also value types. There's nothing about a pointer itself that inherently implies ownership. That's something we put on top of it. The pointers themselves, they're just an address, just a number. And they are value types. And making sure we remember that is also going to help us, because pointers are one of the things that makes this quite tricky. So, okay, the 3 phases: construction, assignment, destruction. Now, that's fairly easy to hold in your head. It gets a little bit more messy from here. There's 8 different ways that we can deal with these. They break down a little bit. So construction, well, we've got the default constructor, easy to understand. Custom constructor is just when you're passing arguments in that you want to use to initialize member variables, that sort of thing. So just whatever you write there. You can consider the default constructor a special case of that. And then we've got this sort of split between copy constructor and move constructor. And then we've got the copy assignment operator and the move assignment operator. So we've got this extra dimension here, copy and move. And then finally, just one destructor, nice and simple again. So all of these, except for the custom constructor, are what we call special member functions. And they have special properties. Mostly that the compiler will generally write them for you if you give it space to do so. And this is a good thing. This is something we want to happen. But we need to understand how it happens or what it does when it does do that. So in the ideal case, we shouldn't have to implement any of these. And that's when we get the gold standard. And when we don't, we're going to need to know how to implement them ourselves. So this is where that warning comes in. This is where it starts to get complex. But just bear in mind that when we get over this hump, there's going to be a nice, easy run the other side. So something to look forward to. So let's go down the rabbit hole. Let's go back to our gadget type I introduced earlier with the pointer. So simplest possible class is an empty class, of course. We can instantiate one of those as a value type on the stack. It doesn't do anything, but it works, and it's easy to reason about. But not very useful. So let's give it a data member, an integer. Again, we know how ints work. So we also know now how our gadget type works, because it effectively inherits what it can do from the integer. What do I mean by that? Well, let's ask the gadget what the value of its integer is and try to print it out to a string. So think for a moment what this is actually going to do. And you're probably right that yes, it is undefined behavior because we haven't initialized the integer. We know how ints work. If we don't give them an initial value, they just take garbage from memory. Put them in the class doesn't change that automatically. The compiler has written a constructor for us here, a default constructor. And it's effectively called the default constructor of an int. It doesn't have one, so that's why it's effectively a no-op. So, and I should say, just to save a little bit of clutter, first of all, I'm making all of these things public. so I don't have to write accessors, that sort of thing. But I'll even go as far as, instead of a class with public first thing, I'm just going to go straight to a struct. But I'm only doing that for exposition purposes, because I'm going to try to fit a lot of code on slides here. All right, so let's add a constructor. Default constructor. No arguments, and it initializes our integer to 0. Hope you're familiar with how member initializer lists work. It's initializing I to 0, and that works. Now we get a 0 printed out, just as we expect. We've actually got slightly better than Aurora integer now. We've got one that initializes itself. Great. Of course, we can also write that as a default member initializer. And this is better for a number of reasons, but in our case here, because now we haven't had to write that default constructor. So by writing the default constructor, we're taking on that responsibility. This allows us to give that responsibility back to the compiler. So that's great. Okay. What else can we do? What if we don't actually want a default value? We always want to initialize it with something valid. We can do that as well with a custom constructor. So now we pass in an integer, we use the member initializer list to initialize it, and we're good. Great. But something that may be a little bit surprising here, if you're not familiar with C++ at this level, is that having done that, having written the custom constructor, we now no longer have a default constructor. If we try to default construct our gadget, now we're going to get a compiler error. So the compiler-generated default constructor is now disabled. It no longer exists by writing a custom constructor. Could be a little bit surprising. And that's true even if we reuse that default member initializer. So this is the first of some principles to do with special member functions. So the compiler will generate special member functions for you where it can. We already just mentioned that. But defining some of the special member functions, and also the custom constructor, which remember is not a special member function, can actually interplay with what actually gets generated, and maybe sometimes stop certain things from being generated or deleted. So something to bear in mind, and a little bit of a minefield to navigate. We're not going to go too deep on that at this level. It's just something to be aware of for now. So, okay, let's maybe add our default constructor back in so we get around that problem. And we could do it this way. This is called an explicitly implemented default constructor, because we've explicitly written the body now. Not the compiler doing it, it's us. In this case, it's doing effectively the same thing as the default constructor would have done, the compiler-generated one. So it's actually better to let the compiler still write that for you. And you can do that explicitly by writing equals default. Very useful to get the compiler-generated behavior back, even if it's the same as in this case. Okay. So what if we copy one of these gadgets? We haven't written a copy constructor, but it just works. Because again, the compiler has generated a copy constructor for us that does the right thing. We're actually pretty good now. And copy assignment would work as well. Actually, the other way around, this is copy assignment. So, all good so far. All right. Let's do something a little bit different. And I'm going to add a destructor and some other bits, but talking about the destructor first. We know how destructors work. In this case, all we're going to do in the destructor is just write something out. We're writing something out in the constructor as well. I'm sure we've used this pattern before. But I've also got this extra bit. There's a global integer at the top that we're incrementing in the constructor. We're effectively giving ourselves an instantiation number so we can try and keep track of things. And I'm only doing this for the purpose of keeping track of what's coming up. Easy to lose track. So don't do this at home, but that this should work. And there's our explicitly implemented destructor. Oh, this is what it prints. So obviously the constructor runs first, prints the value of I, and then we explicitly print I, and then the destructor runs. Hopefully, as we expected, no surprises so far. All right, now it starts to get more interesting. We want to hold one of these gadgets in another class we're going to call widget. We've also got a string and an integer. Now we said we like strings and integers, they're value types. Nice and easy to reason about. That shouldn't be a problem, should it? And pointers, they're also value types. So what happens if we just print these members out straight away? Well, the string has a default value, empty string. The integer doesn't still, we already discussed that, and neither does the pointer, so they're garbage values. So again, we want to add a default constructor. We're going to initialize our pointer to null pointer, and now we get the expected results. Okay, not so interesting so far. Let's give it some real values. We do it a couple of different ways. So we've got the default member initializer for the string, giving it a name. And then we're going to use the initializer, the member initializer list, to initialize the integer to 42, and our pointer to a new gadget. We're creating it on the heap and storing it in our pointer. Okay. And that all works so far. Or at least it prints the right results. But you can see our gadget that we just created, the constructor's fired, because we've seen that log out. But we haven't seen the destructor because, of course, we haven't deleted it. I'm just going to rearrange that so that we can fit the next bits in. That's just the same. So, of course, we add a destructor. That's what they're for. Cleaning things up. Easy, yeah? We delete in the destructor, and we're good. And sure enough, that now prints out what we expect. Our gadget's been deleted, destructor's called, memory's cleaned up. Perfect, we can go home. Not so fast, because what if we copy our widget? Remember, the compiler has generated a copy constructor for us that's just copying the values. Pointer is a value, so what's happened to the ownership? If we run that, not so good. Pointer being free but not allocated. Yeah. Because now we've got two destructors trying to destroy the same pointer, or the same heap object. Okay, so we're going to add a copy constructor now. So, if you haven't done it before, this is how you add a copy constructor. Take it by const ref. Can take it by ref as well. Not advisable these days, so always by const ref. And all we're going to do is just copy the members across as the compiler-generated version would have done, except for we're going to do something different for the pointer. I'll drop that bit for the moment. We're going to create a new gadget on the heap and construct that with the existing gadget so it gets a copy. Straightforward, I think. And that seems to work. But we've only got one gadget in the constructor log. Or only one gadget constructor in the log, should I say. And that's because we didn't implement a copy constructor on the gadget. So it's still using the compiler-generated one. So we can fix that, and then we can see, I won't actually show the code, but now we get that printed out as well. So they add up. We've got two constructors and two destructors. So far, so good. So that was copy construction. What about assignment? Now we're back to our double deleted object again because we don't have an assignment operator. Again, it was compiler generated, did the wrong thing. We're going to need to address that ourselves. So we're going to write an assignment operator, copy assignment operator. Like the copy constructor, it takes our widget by const ref, also returns a widget by ref. It does much the same thing. It's going to assign values from the other object to our members as the compiler-generated one would have done, except for the pointer, where we're going to create a new one on the heap, invoke its copy constructor, as we did before, and we're good. And it seems to work, except, of course, we're missing a destructor again. Because we created a new object and assigned it to the pointer, but the old object, now nothing's tracking it. So what we should have done was delete the old one first. Okay? So far, so good. But easy to miss if we weren't actually checking these logs, because it seemed to work, just leaked. And then there's the logs. Okay, what about if gadget froze when you construct it, or if we're out of memory, so new froze? Well, we just deleted our old pointer, and now we don't have a new one, a new object to assign to it. So one way around that is to create our new object, assign it to a temporary pointer, then delete our old one, and then we can assign the new one in. And that works. So I didn't show the throwing example, but that does actually solve that problem. Not a great solution, but it does solve it. Okay. I think that was just the same slide again. What about, sorry, misspoke. It was a little bit subtle. What I changed there was we're now assigning our original widget to itself. And you can do that, perfectly legal, and it can happen. Except our code now breaks. Well, it doesn't fully break. Again, it seems to work, but what it's now doing is an unnecessary heap allocation and copy. It's creating a new copy of our gadget, which you didn't need to do. So we can guard against that. Easy enough. In some cases, it's more dangerous. Here it was fairly benign, just a performance impact. But we should do that as well. And now we've got a little bit less code because we're omitting that copy. Okay, it's a good time to take a pause and see where we got to so far, because we've written a lot of code. The font's getting smaller, and the people at the back are probably finding it harder to read. So this is our widget class. And you can see we've got a copy constructor, we've got a copy assignment operator, and we have our destructor. We've had to write all of those things, and the assignment operator was particularly tricky to get right, and maybe we're not even quite done yet. But we had to do all of that because we introduced this pointer that had ownership of some memory. We're managing a resource. And when we're managing a resource, we're going to need all three of those member functions, those special member functions. We might need some more as well. We're not done yet. But this is called the rule of three. So one of the guidelines that's going to make it easier navigating this is whenever you're managing a resource, if you need any one of those special member functions, then you probably need all three. There are some exceptions. It's a guideline, even though it's called a rule. But follow the rule of three. Now, there may be some of you thinking, oh, the rule of three, that's outdated. Yeah, C++11, we've now got move constructors and move assignment operators, and now it's the rule of five. And we will get there, I promise. But it's worth still thinking about the rule of three, because actually, the move operations are not necessary all of the time. So don't make life hard for yourself if you don't need to. The rule of three can still get you there. Okay. Forgot what I'm showing here. Just zooming in, that's right, we're not quite done on the assignment operator. There's a little bit more we can do. This is where we got to. The reason I put the copy constructor up as well is just to note that there's maybe a bit of redundancy there, a bit of code duplication. It's doing the same thing in slightly different ways. It'd be nice if we could share that somehow. And we can. This is how we might do it. So we're going to create a temporary widget, copy constructed from our incoming other widget. And then we're going to swap all the members in. So swapping is just going to take the value from one, put it in us, and then take our value and put it in the other one. A couple of things to note here. First of all, we've got that using std swap. It's not just because I'm being lazy, although I am. There's actually a real reason to do that. And that's because some types may have their own specialization of swap in their own namespace. And if they do, doing it this way, we've got std swap to fall back on, but otherwise it's going to choose the one it finds by argument-dependent lookup. That's another topic we're not going to go on to now. So if that doesn't mean anything to you, just trust me on this. When you do these swaps, do using std swap first and then do an unqualified swap, and it should always do the right thing. So that's another little rule to bear in mind. The other thing to bear in mind here is you might be thinking, if you know std swap, that it will actually do a member-wise swap. So you could do swap on the whole widget. The problem is we don't actually have a move constructor here, and std swap is implemented in terms of move. So it's going to call the copy constructor, which we're sort of implementing here. So it's going to be a recursive call. So for now, we're going to do member-wise swap. If we implement a move constructor, we may be able to implement this differently, but we're not there yet. Another thing to note here, nice side effect, is this gives us what we call the strong exception safety guarantee. That means that if an exception is thrown at any point during this assignment, we are guaranteed to have the original value that we had. We're not in some halfway state. The weaker form, the weak exception guarantee, as long as we're in a valid state, we're okay. And most of the time, that's okay. The strong guarantee is quite nice. And it just drops out of this. This is called the copy and swap idiom. Okay, let's carry on. Go back to our fuller example. Then we've tackled the rule of three, the copy operations. Let's have a look at moving. So, move semantics, R-value references, another relatively complex and advanced topic. I'm going to have to assume that you'll have some familiarity with it. If not, there are other sessions that will fill you in on that. But bear with us. So, if we do std move on our first widget, we are saying we can actually take the guts of that object now and use it ourselves. We don't have to make copies. So, if we do that with our current implementation, it actually works. It's fine. This is what I was saying earlier. If you do a move and you don't have a move constructor or a move assignment operator, it's going to fall back to the copy operations, and they will just work. They're just going to be less efficient. So let's be more efficient and implement a move constructor. So here's a move constructor. We're going to do a member-wise move, the string, the int, and the pointer. And that all seems to work. It compiles. Doesn't actually do the right thing at runtime. Hopefully, obviously, we need to do something with that heap allocated object again. Moving the pointer, it's just the same as copying it in this case. So we didn't actually move the resource itself. In this case, it's actually fairly simple to deal with that. Because for value types, pure value types, you can implement a move as a copy and delete, in the case of a pointer. Sorry, not delete, set it to null pointer. So now the outgoing moved from widget no longer has an object it's trying to delete. So we don't get that double delete. And you can see there's actually less in the log now, because now we're not copying things, that there's less operations going on. Okay, that having to do that null pointer assignment in the body of the constructor maybe feels a bit ugly. Feels a bit off somehow. Everything else is done in the initializer list. Well, we can do that too. And actually, the modern idiom is to use std exchange. If you're not familiar with std exchange, pretty straightforward. The name is a little bit misleading. It's not an alternative to std swap. Actually, it does something different. So std exchange will return its first argument. So in this case, our other gadget. So we assign our gadget from that. But then sets it to the second argument. It's like shuffling the values along. That's what we want. So now other gadget becomes null. Our gadget takes on the previous value. Nice little cleanup. Okay. Another thing we should probably do here while we're looking at the move constructor. Move constructors should generally be no except. Not always, but most of the time you can make a move constructor no except, and so you should, and then you should actually put the no except keyword there. If you don't do that, then there's going to be a big performance penalty if you put these things into std vector and some other types. They will actually check that because vectors have to move things around, and if they can't actually move them, they're going to copy them. So make sure you do put no except there. It's one of the few places that you should just routinely put no except. Move constructors, and as we're going to see, move assignment operators. Another little thing to remember. Okay. Talking of move assignment operators, let's try move assigning. So we did std move and assign the result to a pre-existing widget. Again, we haven't implemented it yet, but it just works because it's falling back on copy. So let's implement the move assignment operator. Here's our first stab. So we move our string. We don't actually need to move the integer. Copy and move are the same thing for ints. And again, we can use std exchange for our pointer. Same reason as before. Great. Okay. And also no except for the same reason. All right. Worked first time. Great. Previously, for the copy assignment operator, we sort of evolved it to that copy and swap idiom. Could we do the same thing here, like a copy and move? Well, we could, but it turns out to just not be worth it. Because remember, copy and swap does introduce a bit of overhead, and the main reason to do it is to simplify things and give the strong exception safety guarantee. None of those things particularly apply here. We're no except anyway. We're not going to be throwing exceptions. We don't need that. And it's actually fairly simple code. So it's not worth using a copy and move idiom for the move assignment operator, even though it's tempting to do so. The whole point of move operations is to maximize performance most of the time. So don't pessimize it by using copy and move. Okay. We've got through quite a lot already. Let's just take stock. And there's too much code to fit it all on one screen, so I'm just going to summarize it here. You can see that we've implemented all of the special member functions: copy constructor, move constructor, copy assignment operator, move assignment operator, and a destructor. And previously we implemented 3 of them for the rule of 3. Because we wanted move semantics, we added 2 more, and that gives us, finally, the rule of 5. So again, the rule of 5, if you need one of these and you want move semantics, then you probably need all 5. Again, if you don't need to optimize for moves, the rule of 3 is actually still available to you. You may only need to implement 3. It's a bit less work. Because this stuff, it can be hard to get right. Hopefully you've seen that by now. But you know what? There's a better answer, and it's right in front of us. Let's simplify our widget a bit. If we just take out that pointer with the resource management, we've got pure value types, well, simple value types now, the string and an integer. And instead of all that cout stuff, I'm going to move that to a print just to save a bit of code, because I can actually put all of the operations now in one bit of sample code. So this is doing construction, copy construction, assignment, move construction, move assignment. I'm even doing a couple of logging some moved from states. And that all gives the results that you would expect. You can check. It's a little bit tricky to match it up. Those spaces are the moved froms, empty strings. It's not guaranteed to be that way. So it is on my machine. Nice and simple. We don't have to write anything. That's what we want. Can we get the management of our memory and still have this? The answer is yes, maybe. Let's do the yes part. That's the best bit. So we could use a unique pointer to manage the memory for us. This is not exactly the same as we had before. This does actually have different semantics. So previously, we had copy constructor and copy assignment operator would actually copy our gadget. We don't have that here. We don't have any copy operations because it's unique ownership. So, as I mentioned before, the properties of your data members, the most constrained form in terms of special member functions, you sort of inherit those. So because we're using unique pointer, we now have unique ownership semantics, unless we explicitly implement those copy operations, which we could do the same way as before, which is still a lot less code. So that's good. I wouldn't show that. We've already seen it. Oh, I meant to show that as well. We can see our gadget constructor in there as well now, but still a lot less going on. So that's a big win. And in fact, this leads to the third rule we want to talk about. We really want us to strive to only have value types or managers, and I'm going to define managers in a moment. But this will give us the rule of zero. And really the rule of zero is what you should be trying to follow as close to 100% of the time as possible. Because the rule of zero says, well, in summary, always strive to have the compiler-generated special member functions do the right thing. And if you only have value types and managers, the compiler-generated special member functions will do the right thing. You won't have to worry about them. But sometimes you do have to explicitly manage memory or some other resource, a file, network, socket, whatever it is. The special member functions are there for a reason, but they should only be used for those specific cases. If there's not an existing library type in the standard library, even a third-party library, always reach for those first. You can still write your own, and then you have to follow the rules we just talked about, but don't mix it. So before we had an integer, a string, and managing some raw memory. And that meant that we didn't get the advantage of the compiler-generated handling of our integer and our string. We had to do it explicitly. So always have your own manager types. If you do need to manage a resource, have a manager type. So a manager type is a generalization of something like a unique pointer, shared pointer, anything that manages another resource and implements the special member functions for you. So I wrote a blog post when I was working at Sonar a year or two ago about the special member functions, the rules of 0, 3, and 5. I did actually go into a lot more depth and down some rabbit holes, so if you do want to find out more, it's worth reading that. There's actually 2 of them. This was the second one, but it does refer back to the first one. But I just want to pull out a chart that I put in at the end, just save me recreating it, where I summarize all the different types of managers, and more generally, the categories of type with respect to resource management. So the simplest ones at the top, are value types. Simple direct values, ints, strings, that sort of things. They follow the rule of zero. Or rather, if you use them, then you follow the rule of zero. Views are non-owning managers. So they do actually deal with raw memory usually, like string view or span, MD span. So they also follow the rule of zero because they don't actually manage ownership. But then you get to polymorphic base classes. They're a little bit different. We didn't really talk about those. You probably will need to follow the rule of 5 or some variation on it. There's an asterisk. I'm not going to go into the details that I went into in the blog post. Basically, follow the rule of 5 for polymorphic base classes. So anything with virtual, particularly pure virtual member functions that you derive from. Then we get into the managers. So the simplest one is a scoped manager. So a scoped manager is non-copyable and non-movable, which means you are following the rule of 5, but you're doing it by deleting copy and move operations. So it is simpler. A delete with the delete keyword equals delete counts as an implementation. So you're following the rule of 5 for scope managers. So they're the simplest types and maybe the least useful. Unique managers, perhaps the most useful. So unique pointer is an example of a unique manager. So it has unique ownership and move-only semantics. So again, we follow the rule of 5, but we disable or delete copy, the copy operations. And we implement move. And finally, more generally, a general manager that does have move and copy and follows the rule of 5. Value types are maybe examples of general managers, like std string, std vector. You can treat them as value types, but they implement that resource management for you. There are examples of general managers that aren't value types in the same way, like shared pointer. Shared pointer, you can copy, you can move, but it's not a value type because it's got shared ownership. So there are some more advanced levels here that I'm going to stop short of going into in depth, but do read the blog post if you want to find out more. And with that, I've actually come to the end of what I wanted to share with you. So thank you very much. And we've got plenty of time if you've got questions, because there's lots that I papered over there. Any questions? So Mike. Yeah. Someone come? Okay, great.
Yes, thanks for the talk. The slide just before the rule of 5 was introduced, it looked like there's a missing destructor, but I wasn't sure if that was a typo or if that was expected behavior.
Hold on, sorry. Got distracted trying to find a slide.
I think it's in front of this. Or, sorry, after this. Ah, yeah.
That one? Oops.
Yeah, just before this.
Actually, this one, yeah. Or the previous one. This one.
Correct, yeah.
Yeah, okay. So your question?
Just, is the missing destructor number 2 here expected behavior, or is that a typo?
Sorry, I didn't quite catch that.
Is the missing destructor here expected behavior, or is that a typo? There's a constructor for number 2, and then there's no destructor for number 2 ever.
You are right. And that is expected because this is a move operation. Okay. So we're transferring ownership. So the destructor for gadget only happens once, but you get the move operation.
Okay, thank you.
Hi. So I was curious if you could elaborate on situations between when you'd use rule of 3 versus rule of 5. And it sounds like rule of 5 often there are performance gains. Are there other reasons besides performance for when you'd want to use rule of 5?
Other reasons that you might still prefer the rule of 5 other than performance reasons. Right, anything that's going to lead you to implement move semantics. In particular, I mentioned the unique ownership managers, so they are move only. So the only way you can use them is to move. Of course, you're probably doing that for performance purposes, but if you're using, say, a unique pointer, then you have now move semantics. So,
Thank you.
Yeah, off the top of my head, I can't think of a more concrete example, but yeah.
Hi. I've seen implementations of the copy constructor where the temporary object was created implicitly by not passing a reference into the copy, and I'm sorry, the assign operator, by passing the assigned object into it using a copy constructor as opposed to creating one on the stack. Is that considered bad form or just not something that you want to show?
We tried to piece together what you said, if I got it right.
If
So,
you go to the slide that
assignment
shows the
operator.
assignment operator.
You're talking about explicitly calling the copy constructor?
So instead of the assignment operator receiving a const reference to an
Oh,
object,
receiving a value. Sorry.
it would be receiving a value.
Yeah. So let me find the slide where I showed. Well, that's one of the examples of the copy and swap idiom. So I think this is what you're talking about. So rather than taking other in by const ref and then copying it into temp, we basically make other pass by value, and now it is our copy.
Non-const.
Sorry?
Non-const and by value.
Non-const and by value. That is now playing the role of our temp. It should boil down to the same code. It's one less line. And from an implementation perspective, it seems to be simpler. The one reason I would say, I'm not saying don't use it, it's a perfectly valid idiom as well. But the one thing to keep in mind is you're now saying something on your interface about what your implementation is doing. So when you have the const ref, from the caller's perspective, it's an operator anyway, so you don't really call it explicitly. But still, when you're looking through the interface, you think, oh, this is just taking a reference in by const ref. It's not going to do anything with it. When you have a value type there, that's just saying something slightly different. 99.9% of the time, that's not going to matter. And so you can probably do that. But it's just one thing to keep in mind. It does actually change the interface a little bit, but it's perfectly valid. Yeah, thank you.
I also have a question about the same slide. When the destructor of the temp widget gets called, I assume the last swap there, it takes the gadget that's within this.
Sorry, this one, did you say?
Yes,
Yeah.
this slide, the last swap. And it will swap it into temp. So when the destructor gets called, what happens there?
Right, yeah, so good question. I didn't really explicitly say that, but so we create the temporary widget, and with all the swaps, we're swapping our state into the temporary. And now the temporary will get destroyed. And so our previous state is now cleaned up, which is probably what we want, because now we've taken on a new state. So we've passed on the responsibility of cleaning up to the temporary object. If we go back to this version, we had to explicitly delete our previous heap allocated object. And that was causing a bit of problem because, what happens if an exception's thrown? We need to worry about that. If an exception was thrown, although by moving the order, did I have that one? I don't think actually I did that slide, did I? If you do the delete, oh no, that is right, yeah. So we've got the temporary variable for the pointer, then we delete, and then we assign. And if an exception is thrown in the middle, we'd be in a valid state, but not the original state necessarily, because we've already changed name and age. Again, we can play with the ordering a bit, but the copy and swap idiom just takes care of all that for us, does all the cleanup for us, just simplifies thinking about it. All we have to do is the swaps. So even though the amount of code is similar, the complexity is much less. So that's the advantage of copy and swap. There's a slight overhead, or there may be optimized out. More so on the move and swap, that's the one to avoid. But copy and swap for assignment operators, I still routinely do that. But you can do it by hand. Did that answer your question? Yeah, thank you.
Thanks for the talk. So I was curious when you recommend explicitly defaulting one of the Rule of 5 you discussed?
When to explicitly default? Good question, actually. I touched on it a little bit, where I said, well, if you're doing the same thing anyway, just let the compiler write it for you. But the general rule is, if the compiler can write it, you should let it write it. There are some cases where, as we said, defining some special member functions or the custom constructor will suppress that generation, but you can get it back by using equals default. And in some cases, by following the rule of 5 or the rule of 3, you're saying, well, I need an assignment operator here, but I know the compiler is going to do the right thing, so just default it. Even if it was going to write it anyway, you're being explicit about the fact that you followed the rule of 3 or the rule of 5. So that's the other case where you might use it, even though you didn't even need to.
So do you advise then that for the Rule of 5, we either default them, implement them, or delete them explicitly to make it more verbose what we're trying to accomplish?
It's a little bit more verbose, but I think it's more expressive. Mm-hmm. In that blog post, I do go into a little bit of a more advanced topic, where there are some cases you might want to go against that rule, but it's effectively following another rule. So have a look at it. There are some exceptions, but generally for this sort of thing, because if you're reviewing somebody else's code and you say, oh, there's some resource management going on here, how do I know they've done it right? It's a good sign if you can see they've considered the rule of 5. It's a good starting point. So you want to signal that, yeah, I've considered all of these, and I think the compiler's doing the right thing. I've not just left it to chance. That's the key.
Awesome, thank you.
No problem. Any other questions? Okay, great. Then I think we can have an early termination. Thank you.